So this one, we're going to do percent error, metric ladder, and scientific notation. So some of it will be a review from middle school, but I want to make sure we have all those basics done. So when substances are irregular shapes, we can place them in a graduated cylinder and measure the displacement of water to find the volume. So that is really nice. You don't always have to, if you have a cube, to find the volume, you can do length times width times height. And then you can get that volume that way. But that can be pretty cumbersome. And in fact, sometimes it's just easier even to put a cube directly in a graduated cylinder. This is just a zoom of a graduated cylinder. Why is it called graduated cylinder? One, it's a cylinder, but two, these are called graduations. These little ones here are minor graduations, so they have small steps. And these larger ones here are major graduations. So on this particular graduated cylinder, the major graduations are 10 and the minor graduations are 1, but you would have to look at each graduated cylinder to determine that. Find the density grams per milliliter. Okay, and this graduated cylinders are typically in milliliters, so that's going to help. Of a substance that measured 10 grams on the digital scale. Okay, 10 grams, so that is our mass. So we have our mass value. Density is mass over volume. So we have our 10.0 grams on the numerator. Now we just need the volume. The image shows the water level after the substance was placed in 60 milliliters of water. So our original height was 60.0. And then it went up to here. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just confirming that they're 1 each. 1, 2, 3, it's between the 3 and the 4. Okay, so that would be 63 point something. You always measure at least one more than what the analog or non-digital thing says. So we don't just leave it 63, we don't leave it 64, we go one more than the gradation. And when you are measuring, you measure to the bottom of the curve. Okay, that curve is called the meniscus. And we measure to the bottom of it just because we have a standard. We could always measure to the middle or to the top, as long as we're consistent across the world. And we have determined that it's easiest to measure to the bottom. It's easiest to figure out and read right there. Why does this happen? This is surface tension. So with capillary action, it tries to climb up the side. So since it's a wider graduated cylinder, this is also probably going to be closer to the actual volume if we were using a whole totally different setup. And it's about halfway between. So I'm going to call this 63.5 milliliters. So it started at 60 and now it's at 63.5. So I'm going to subtract to find the difference, 3.5. I'm adding and subtracting or multiplying and dividing. I'm subtracting. The rule for subtracting is round to the least decimal place. 1 decimal place, 1 decimal place. So my answer has to be 1 decimal place. That is what you are going to do each time you are doing addition or subtracting, round to the least decimal places. So my volume is 3.5 milliliters. So my answer is going to be in grams per milliliter, which is what they wanted, so I don't have to do any unit conversions. 10 divided by 3.5 gives me 2.85714,286. Now, this problem is multiplication or division. It's division, so this one is round to the least decimal places. After each equation, you find the correct sig figs. Okay, so you always adjust after each equation. This guy, how many sig figs? 1. These are trailing zeros because they're on the right. So if I see the decimal, which I do, it's significant. 3 sig figs. 1, 2, because they're 2 non-zeros. So I need 2 round to the second sig fig. This is the first sig fig. This is the second sig fig. So I'm either going to round down to 2.8 or up to 2.9. I look next and it's a 5. So my answer is 2.9 grams per mole. Okay. Now, If you use the triple beam balance in middle school to find the mass value, that is analog. So you would again have to estimate the next decimal place. But since this was on a digital scale, we just record exactly what it says because it's digital, it's more exact. All right, here is our metric ladder. They are not going to give you this on the test, but you tend not to need the full ladder. In fact, this isn't even the full ladder. For the SOL, you need between kilo and milli. King, kilo, Henry, hecto, died, deca, base, deci, centi, milli. King Henry died by drinking chocolate milk. That's how you can set up your ladder. And then you can do your conversions. Number one thing people do wrong is they don't check to make sure it has the same root. Both of these are liters, so we are converting units of volume. We have DL, that's deciliter, not decaliter. So read carefully. Deci just has a D before the L, and we're converting to decaliter. We're going from deci to deca, so we are going up the ladder. How many steps up the ladder? 2 steps up the ladder. So we're going to move the decimal to the left, 2 steps, 200. This is where the decimal is. We didn't see it because it's not significant here, but we still know it's there. 1, 2. So 200 deciliters is 2 decaliters. 1 sig fig is here, so 1 sig fig is there for our answer. How about if we're going to go the other way? This one starts with kilo, kilograms, though. So these are going to be units of mass. We check, they both have the same root, so we're converting from one thing of mass to another. Kilograms to milligrams. Notice there's a bunch of M's too, mega, milli, and micro. Micro's the little script one. We are going down the ladder this time. 1, 2, 3, 4, 5, 6 steps to the right. Move the decimal to the right for each step. Okay. 2.5, 1, 2, 3, 4, 5, 6. Then fill in 1, 2, 3, 4, 5. 2, 5, 1, 2, 3, 4, 5. And then I'm going to go back and add my little commas in. Okay, so 2.5 kilograms is 25,000 milligrams. Sig figs, 2 sig figs, 2 sig figs. These guys are all trailing because they're on the right. No decimal is shown, so they're not significant. They are still important for placeholders for the answer, but I'm making sure that my starting sig figs is my ending. So my answer is still, oh, can't put my commas in the right place now. Is not 25,000. That is 2,500,000. Same setup. Commas do not affect my sig figs. So it doesn't matter where I put them. If I put them wrong or right, it's not going to affect my sig figs. But on my final answer, you can either just put in no commas or put the commas in on the correct locations. Okay, so you could write this or 2500000, or you can put it in scientific notation. We know the decimal place is there. 1, 2, 3, 4, 5, 6 places. 2.5 times 10, and it's a big thing, so it's a positive decimal place. 2.5 times 10 to the 6th. Hey, wait a second. I remember 6 from the beginning. 1, 2, 3, 4, 5, 6. Yep. So you could have just said 2.5 with 6 hops to the right. If you wanted to do hops to the left, 200 times 2 hops to the left. Now this would not be accepted as an answer because it's not scientific notation, but technically it is an answer. All right, so what do we have here? Which of these best completes the conversion table? So we got to go back and have that metric ladder. So you might want to write down King Henry died by drinking chocolate milk onto your paper at some point so you don't forget. 1 kilometer is equal to 1,000 somethings. That's 3 hops we did to the right. 1, 2, 3. So that is just going to be simply 1 kilometer is 1,000 meters because the roots have to match. 1 meter is 100 what? So 1 meter is here. And we have 2 hops for 2 zeros, 1, 2. 1 meter is 100 centimeters. 1 kilometer is 1,000 millimeters? Nope. 1 kilometer is 1,000 meters. Okay, that might be right. 1 meter is 100 millimeters. Nope. 1 kilometer is 1,000 centimeters. Nope. 1 kilometer is 1,000 meters. 1 meter is 100 centimeters. Double check. Everything matches because it could have been that you did an error and messed it up. So make sure you only got one proper one. If you're like, oh, I'm still not so sure about this, go back the other way and take kilometers and convert to millimeters and see if you get 1,000. And you'll be like, oh, I don't get 1,000. 1 kilometer. And I want to go to millimeters. 1, 2, 3, 4, 5 is 6 hops. 1 and then 6 hops. 1, 2, 3, 4, 5, 6. Fill that in. 1 kilometer is 1,000,000 millimeters. So you can check it either way you want. And you can always watch this again and hit pause and check out your answers. So scientific notation, what we talked about at the beginning, it always has a number in the 1 spot. Okay. No number in the 10 spot. So there should be nothing here. Okay. And then it'll say times 10 to the y. This y has to be a whole number. So this first guy is not incorrect scientific notation. Anything else messed up with any of the other ones? Number in the ones, whole number here, this guy is correct. Number in the ones, whole number here, it's just the negative, this guy is correct. And yes, you can have numbers in the tenths, the hundredths, the thousands, just not in the tens spot. Oh, this guy has a number in the tens, not correct. This guy, number in the ones and the exponent, it's just written in calculator format. 9 times 10 to the negative 4 is how you'd write it out if you were on paper. But 9e to the negative 4 is how you'd write it in Canvas or on your calculator. Okay, so that's scientific notation. So hopefully you can identify that. But now how do we make that expanded? 4 times 10 to the 3. 10 to the 3 is positive. So that means it's going to be a big number. So we need to move the decimal to the right. How many times? 3 hops. 4, the decimal's here, 1, 2, 3. So that expanded is 4,000. 1 sig fig, because you don't count sig figs after the X. 1, the first sig fig, and we don't count that. This does not mean the answer is 4. The answer is still 4,000, but it only has 1 sig fig in it. It has to match the sig figs we started with. 5.0 times 10 to the negative 3, that is negative. That guy means we're moving to the left on the scale, on the number line scale, because we're going to be making the number smaller. 5.0, how many hops to the left? 3. 1, 2, 3. This is the new decimal place. 0.005. 0.005. Sig figs, significant, trailing 0. I see the decimal, significant, so my answer needs 2 sig figs. Leading, never significant. Non-zero, always significant. I need a trailing, so I got to add that other 0. So there is my correct answer with 2 sig figs. 9e to the negative 4. 9, small number or negative number, so we're making it smaller. So we're going to take that decimal place to the left. 1, 2, 3, 4. 0.0009. 0.0009, and often in chemistry, yep, we'll even write it like this, but to make your math teacher happy, put that there. These are all leading zeros. They are not significant. So we only have 1 sig fig, and we only have 1 sig fig here, because even though there's not an X, we don't count any of those sig figs that are placeholders. So that's how you go from scientific to expanded. Now we have expanded and we want to make scientific. Always a number in the 1 spot, never a number in the 10 spot. So where is our target value? Our target decimal place is right there, because then we'll have a number in the 1 spot and no number in the 10 spot. 1, 2, 3, 3 hops. So 5 times 10 to the 3. What type of 3? It's a small number, so it's a negative. This guy has how many sig figs? Leading zeros, that's the whole bunch of leading. Everything to the left of a non-zero, not significant. 5 is significant. What about this 0? I see a decimal. It doesn't matter, a decimal is all the way over there. Trailing zeros are significant here. So I got to add a 0 here. 5.0 times 10 to the negative 3 is the number in scientific notation. How about this guy? Where is the decimal? Where is our goal? Right here, because then we have a number in the 1s and nothing in the 10s. 1, 2, 3, 4, 5, 6. So it's 3.040000 times 10. How many hops? 1, 2, 3, 4, 5, 6. Is this a big number or a small number? Big number, so it's positive. Now let's look at our sig figs. Non-zeros are important. Trap zeros are important. These are trailing zeros. They're zeros to the right of the last non-zero. Do I see a decimal? Nope, not significant. Doesn't matter that I see a comma. I can only have 3 sig figs in this answer. So I underline the 3 here. That's the first 3 sig fig. This 0, it's trapped. So this is my second sig fig. The 4 sig fig. I look next, it's a 0. So I'm going to round down 3.04 times 10 to the 6, or 3.04 e to the 6 is my answer. 23.45. Here's my decimal. Where's my target? 1 hop to the left. 2.345 times 10. I made the number smaller, so I need a positive here to make it bigger again. How many hops? 1. 2.345 times 10 to the 1. You can always then type this into your calculator and see if you get the original answer back. You can use your calculator on the SOL. Have it help you out. You can do that with most of the problems. Some of them will give you expanded or otherwise, but especially these shorter ones with a small exponent will give you the answer. Check. 5. That one's weird. 5. It's already in its target spot. 5 times 10 to the 0, because 10 to the 0 is 1. So that is how you would write that number in scientific notation. Speed of light is about 300 million meters per second, which is the correct expression for the speed of light in scientific notation. Okay, this first one has a number in the 10 spot. We can't use that. Number in the 10 spot. Can't use that. So we're between these two. Doesn't even give us a negative or a positive. We know it's a big number, so it's going to have a positive exponent. But they don't even test us on that on this one. So we just need to know, is it 7 or 8 hops? Where's the decimal? Right here. 1, 2, 3, 4, 5, 6, 7, 8. 8 hops. And there we go. What is 10 to the 4.5 in expanded and scientific notation? So 10 to the 4.5 is in an improper fraction. We do not leave decimal places in there. So it's like an improper fraction, sorry. So what do? Put it in your calculator. 10 to the 4.5, or if you're using Desmos, 10, hit the AB button and 4.5. Okay, or you could have 10 to the X button. In that case, you would type 4.5 and then hit your 10 to the X button. And always try these out on the video to make sure you're getting the same answer as me to confirm you're using your calculator correctly. This guy gives me 31,622.7766. Here is my answer. It does go on. I'm just writing out the first couple. Okay, this is it in expanded notation. If I wanted to be particular, I would have it just to 2 sig figs. So your answer, it might tell you on the SOL is 32,000. What is it in scientific notation? Where is my decimal? Here. Where do I want it? Here. 1, 2, 3, 4. 3.16 times 10 to the 4, positive 4, because it's a positive number, it's a big number. 3.2 times 10 to the 4th, if I'm going to do that, 2 sig figs. All right, accuracy and precision. Accuracy, how close to the actual value. So when you're dealing with accuracy and they give you a number of trials, then make sure you find the average. Accuracy, if you have multiple trials, find the average. If you don't have multiple trials, you don't have to find the average because you only have one value you're going to compare against the book value. But we have multiple values to compare against the book value, so we're going to find the average. Okay. Number 2, we're going to find the average. Find the average. How do we find the average? Add up all these guys, so take the sum of that and divide by how many there are. So you can check with your calculator if you're not sure how to do that. Okay, these count as adding and subtracting, so I round to the least decimal place. All right, so now I have 8.1 compared to a book value of 8. So my accuracy might be pretty good. I'm going to do one further calculation in a minute to make sure. Okay, 1, whoa, my accuracy is not good. My book value is 5, not accurate. That one's definitely clear. This guy, 100. Okay, so this one's probably accurate, but I'm going to do another step to make sure I have it. Precision is the range, how close it is to your own value. So how close is 7.6 to 8.7 to 8.3 to 7.7? Doesn't matter if it's accurate or not. Precise just means compared to your original numbers. So we find the range, the biggest minus the smallest. So for this first one, 8.7 minus 7.6 gives us 1.1. So all the numbers are within 1 of each other. I'm not sure if that's precise or not. I'm going to keep going. These guys are 0.06. Okay, I'm going to say this guy is precise. So this experiment number 2 is not accurate at all, but my measurements are precise, which means I'm doing the same exact thing very well. I'm just doing the wrong same thing. I have an error in what my procedure is telling me to do. So I'm doing something wrong. It could be as simple as not closing the door on my mass balance and the air current's messing it up. It could be as simple as I'm adding too much water to each test and it's throwing something off. So it doesn't have to be anything big. It's precise, meaning I did the same exact thing each time. It's just not accurate. It's not getting anywhere to the actual value. All right, last guys. 1.5. Okay, so now when I'm looking at these two, if I have to rank how precise these are, this guy's off by a count of 1 when it's 8. So that means technically it could be going down to 7 or up to 9. Okay, that's not exactly how it works, but it's a good way to measure it. All right, this guy is off by 1.5, which means the worst case is it's going down to 98.5 or going up to 101.5. Which one is worse? This guy is worse. This is not as precise. It seems like it is because it has a smaller number, but you got to compare it to what we're dealing with. We need to be around 8, and we're 1 off from around 8. Whereas up here, we're 1 off from 100. So getting a 98.5 on a test, you're going to go, okay, yeah, that's not a big deal. It's out of 100. If it's out of 8 and I get a 7 on the test, a 7 divided by 8 is going to give me 87.5%. So I'm going to lose a whole letter grade beside not just a couple points off. So that's, you can always compare it back to your grades to see if you're deciding that way. Okay, now let's go one more step because accuracy really should be compared with percent error because that is how far off you are from the actual value. All right, so when we do this, if you have an average, you put the average here, 8.1 minus the theoretical, which is 8 over 8. So my answer is going to be, what are these things? Absolute values. So no matter what you get in the numerator, make it positive. So 0.1 divided by 8 times 100, 1.25%. Okay, so this guy is pretty accurate because it's pretty close to its book value. The next guy, we got a measured value of 1 and a book value of 5. Okay, we already know, we don't even really have to do this. This percent error is going to be huge. 1 minus 5 is -4. We make it positive. 4 divided by 5. This guy is off by 80%. Totally not accurate. This is a huge percent error. But we knew that already. We knew it wasn't going to be accurate. This one's pretty much a low percent error. How about this guy? This guy has a percent error of 0%. I don't even have to do the calculation because I got exactly what I was supposed to get there. Right. How many different elements are involved in the chemical reaction? Remember, the chemical symbol always starts with a capital letter. So Ca is only one element. And you can look on your periodic table because you can use it in all parts. That's calcium. There is no capital H, capital O element. Why? Because each capital letter gives you a different element. So capital H, this is the element of hydrogen. And here is my element of oxygen. So you know you can actually stop right here because of the law of conservation of mass. We can't have different elements on the left and on the right. So we are only going to have 3 elements. But let's make sure we understand and double check over here. We have calcium, oxygen, hydrogen, hydrogen. Good, we only have those 3 elements. We just have hydrogen showing up in 2 spots. We have more atoms that may be going on over here. Let's check. 1 calcium, 1 calcium. Same number. Why? Conservation of mass. So maybe we are going to have the same number of atoms. 4 atoms of hydrogen, 2 atoms, and 2 atoms. Oh, conservation of mass. Matter cannot be created nor destroyed. We have the same elements on the left as on the right. We have the same number of atoms of each element on the left and on the right. What is something that doesn't follow conservation of mass? We have 3 moles on the left and 2 moles on the right. Moles are not mass, because everybody has a different mass on the periodic table. All right, if P is 300, V is 5, N equals 0.25, R is 8.31, what is the T? So even if you haven't done this unit, you can still evaluate here. Whenever you see variables and they don't give you how they're connected by multiplication. So my P value 300, my V 5, my N 0.25, my R 8.31, my T is what I'm solving for. So 300 times 5 equals 0.25 times 8.31 times T. If you have one equation, which I do, you can only solve it if there's only one unknown, which I have, one equation and one unknown. So this is solvable. So go back and put on your algebra brain. What's the first thing you do? Combine like terms. 300 times 5, 1500. On the right, 0.25 times 8.31, 2.0775 times T. Do not simplify now. You can only simplify at the end of the whole equation. This is connected by multiplication, so I'm going to divide. What I do to one side, I do to the other. So on the right side, that 2.0775 divides out and becomes 1. And on the left side, 1500 divided by 2.0775 gives me 722.021661. This is our calculator answer. But if we want it in the proper sig figs, significant, trailing zeros, I don't see the decimal place. 1 sig fig. 1 sig fig. Leading zeros, not significant. 2 sig figs. 3 sig figs. I'm doing multiplication and division round to the least sig fig, so rounding to 1 sig fig. Underline the first sig fig. 7 is a sig fig, so I underline. What place is that? It's in the 100 place. So I'm either going to round down to 700 or round up to 800. I look to the next number, it's a 2. So my answer here is 700 if we're rounding to the proper sig figs. All right, if 2 legs of a right triangle are 30.5 and 10.0, what is the hypotenuse? What do we have to remember here? Pythagorean theorem, a squared plus b squared equals c squared. Yep, it can come up anywhere. It does not matter which is a or b. I'm just going to make a 30.5, but you could do it the other way, b 10.0. I got to solve for c. So parentheses, m exponents, multiplication, division, addition, subtraction. So I got to get rid of my exponents first. 30.5 times 30.5 or 30.5 squared, either way you want to write it, is 930.25 plus 10.0 squared is 100 equals c squared. 930.25 plus 100 is 1030.25. That's equal to c squared. I can't leave it c squared. I want the value of just c. So I got to do the opposite. The opposite of c squared is square root. What do I do to the one side? I do to the other. And that is going to give me 32.09750769 and so on. 3 sig figs because trapped zeros are important. I see the decimal, so trailing zeros are important. I'm going to round my answer to 3 sig figs. 3 is significant because it's non-zero. 2 is significant because it's non-zero. This is my third one. It's a trapped one, so it's significant. I'm either going to round down to 32.0 or round up to 32.1 because I'm rounding to the nearest 10th. And this is a 9, so 32.1 is the length of the hypotenuse. All right, if A over B equals C over D, let's rewrite that so it's a little bit prettier. A over B equals C over D. And A is 5, B is 3, C is 4.25. What is D? All right, let's rewrite again. 5 over 3 equals 4.25 over D. You'll want to use some sort of cross multiply and divide method on this one because the D is on the denominator. You cannot just divide by 4.25 on both sides and call it done because that's still going to leave your answer in 1 over D. So the two things that are identical on the diagonal, that's a multiply. The odd one out is the divide. 4.25 times 3 divided by 5 gives me 2.55. 1 sig fig. And I'm doing division. So this is actually going to round up to 3. They may just want a full answer there. They may want it rounded to the sig figs. See what the problem says. All right, if I take the benchmark and get 15 incorrect out of a total of 43, assuming 1 point per question, what is my grade? Part over whole. Almost everything, if you're having to do a comparison, is part over whole. Percent error is not. Finding your multiplier is not. Almost everything else is part over whole. So the whole thing is work 43. And my part that is positive is 43 minus 15. Make sure you use parentheses there so it divides at the right time. And that is going to give me 0.65. That is my decimal. To change to a whole number, you multiply by 100%. In your calculator, you just say times 100. So I got a 65% on my benchmark, which is often passing. Depends on the year. And that's all for today.